All right, everyone. So this lesson is 2.1.4. It is circuit simplification with the use of Boolean algebra. Now, there's a couple of different methods to simplify circuits. Boolean is the first one that we're going to look at. We will follow up with two additional methods as we progress through the rest of this unit. But Boolean algebra is kind of the most common way to simplify a circuit, though it is not my favorite. So this presentation is going to explain the concepts of Boolean algebra and look at some of the application for circuit simplification from expression statements. So let's start by talking about what Boolean algebra is. So Boolean algebra is a mathematical technique that provides the ability to algebraically simplify logic. So this is just a very different form of algebra. The same basic principles apply. There are rules that guide how we simplify the circuit and how we apply the theorems. But these simplified expressions result in a logic circuit that's equivalent to an original circuit, but uses way fewer gates. And there's a couple of reasons we want to have fewer gates. One is that technically every gate that we have in a circuit causes a delay. We don't really see it in simulation the way we would in real life, but every time an electrical signal has to physically go through an IC chip, it slows down the signal just a little bit. So fewer gates mean faster circuits. Additionally, more gates mean more money. Every IC chip costs a certain amount of money, and the more IC chips you have, the more gates you have, the more expensive your circuit's going to be. So let's take a look at the first four theorems that are on this slide. So these are the single variable and function. So what this is saying is that we have a single variable and we are specifically looking at and as the function. So anytime we are taking a single variable, in this case x, and multiplying it by 0, 1, or itself, we get a certain result. So if we have x times 0 is 0, x times 1 is x times x would give us x, and x times 0 is, or x times x, it can also be 0. Well, x times x naught is 0. Misspoke. So underneath that, you will see it laid out in the form of a gate, and then you will also see an example of it in a truth table. This probably looks really overwhelming right now and a little bit confusing. It will make more sense when we walk through how they're actually applied to an expression statement. So these are our single variable or functions. So the last slide was and, this slide is or. So we have theorem 5 through 8 that are single variable and focus on or. So again, in this case, our variable is x. And so anytime we have x or 0, we get x or 1 is 1, x or x is x, and x or x naught is 1. So if we look at the truth tables, you'll see lines crossed out. That is just exemplifying where these theorems are true inside of those truth tables. And then theorem 9 is when we deal with inversion. So basically this is saying that x naught is equivalent to x. That's basically saying if we have x and it's inverted to x naught, and then it's inverted back, it's x naught, and x naught is equivalent to x. I know that seems silly because it should just go back to x, but in algebraic terms, this is how we would break that down. So I'm going to walk you through this first example, and then I'll let you guys problem solve through the other three that are in this presentation. So this one is just to simplify the following expression and note the Boolean theorem used at each step. It's really important as you go through that you write down what theorem you're applying. So that way, if your end final expression statement is not totally accurate, you have a way to go back and track and figure out where something went wrong. So the first expression we're going to look at is A, B, or C naught, D. Now I'm sure some of you already are recognizing there's two A's in that first expression. We haven't seen that yet, and part of that is so we can simplify it. So how do we use this? Well, when we start going through the simplification process, we have to first perform any inversions of single terms first. So if we have any x naughts, y naughts, etc. And then we have to perform all the operations within parentheses. So just like in algebra, when you're balancing equations, we have an order of operations. Same thing here, they're very similar. Then we perform any and operations before any or operations unless our parentheses indicate otherwise. And if an expression has a bar or an overline, we perform the operation first and then we invert it. So here's that solution to that first problem. So we had A, B, or C naught, D. we started out by applying Theorem 3. So Theorem 3 is applied to that expression, and you'll notice that what happens is we lose this second A. So in our second step here, we have A, B, or C, C naught, D. So that results in our first step of simplification. We then applied Theorem 4. Once we applied Theorem 4, basically C and C naught canceled each other out. So then we have A, B, or 0, D. Then we applied theorem number 1, which got us A, B, or 0. And then we had just A or A, and then we just have A and B because 0 is 0. So our final expression for this theorem is F1 is equal to AB. Now that might have blown your mind and you have no idea what just happened. Take a minute, rewind, watch through, look at the theorems as we're going through so you can see how they're applied, and then we'll move on. All right, so let's take a look at example number 2. I did not change the title there, but that's fine. So simplify the following Boolean expression and note the Boolean theorems used at each step, and then we're putting the answer in SOP form, so at least that matches. So this expression is longer. This one is B, B, C naught, or B, C naught, C naught, or A naught, B1, or A, B naught, 0. So we have this giant expression, and the first thing we're going to do is we're going to apply Theorem 3 twice. So we're looking at, so then we end up with B, C naught, okay, so those B's condensed, B, C naught, those C naughts condensed, or A naught, B1, nothing changed there, or A, B naught, 0, nothing changed there. After we apply Theorem 3 twice, we then apply Theorem 7, which then results in B, C naught, or A, B1, or A naught, B1, or A, B naught, 0. So those B, C naughts as identical terms come together. We then apply Theorem 2. So we have B, C naught, just like we did before, but this time we have A naught, B. That 1 comes out of our expression, and then we are left with or A, B naught, 0. Theorem number 1 is then applied. So we have B, C naught, no change there, or A naught, B, no change there, or 0. So A, B naught came out of the expression. And then the lastly, Theorem 5 is applied. So we have B, C naught, or A naught, B. So our final expression ends up being B, C naught, or A naught, B. So here are a few more theorems. There are several Boolean theorems. All of these are actually placed into a document in our General Resources tab. So if you want to get that and screenshot it into your engineering notebook so it's with your notes, that's fine. The last slide of this presentation also has all of them. So looking at Boolean theorems in terms of commutative law, we have Theorem 11, which is an AND function, and Theorem 12, which is an OR function. So this is X and Y equals Y and X, and Theorem 12 states that X or Y equals Y or X. So basically we're just saying that even if we flip those back and forth, so Y is first instead of X first, they are equivalent to each other. We also have associative law. So Theorem 13 and 14 are associative, and they deal, and the AND function is X parenthesis YZ is equal to parenthesis XY parenthesis Z. So basically it's saying that we can shift those parentheses and we're going to end up with the same result. And then for the OR function, we have X or parenthesis Y or Z parenthesis is equal to parenthesis X or Y parenthesis Z. So again, that shifting of those parentheses to create equivalent statements. And then we also have 15 and 16, which are distributive. So just like in algebra, you can distribute a variable through an expression to remove parentheses. So for the AND function, we have X parenthesis Y or Z parenthesis is equal to XY or XZ. So we can distribute that X through that statement to create two equivalent smaller expressions and remove the parentheses. And then the OR function works in a similar way. If we have parenthesis X or Y parenthesis and then parenthesis W or Z, we can then distribute throughout, so then we end up with XW or XZ or YW or YZ. So there we took the X and Y and distributed across to end up with 4 individual pieces to that expression statement versus the parentheses. So here is example 3. I just put everything up here because it is very long and I wanted to walk through it with you. So you're going to simplify the following Boolean expression and note the Boolean theorems used. So this expression is F3 and it is R naught T or parenthesis R or S naught parenthesis R naught or T parenthesis. So the first step it has us use here is theorem 15. So what we're looking at is we are removing those parentheses from the expression. So if we look, we go from the original expression to R naught T or R naught or RT or S naught R naught or S naught T. So we went through and we broke this down into individual pieces for this expression. After we've done that, we can then use theorem 4. And that results in R naught T, so no change there. Then we have a 0 up here, and that is because R and R naught cancel each other out to create that 0. Or RT, no change there. S naught R naught, no change there. S naught T. Something you may begin to notice is that when we apply a theorem, it's only actually affecting one section of the expression statement. It's really important that we don't blaze through and do multiple things at the same time, because again, if our final expression isn't making sense and we collapse things too rapidly, we won't be able to backtrack to figure out where our error occurred. So then we applied theorem 5. So if we look at applying the application of theorem 5, we have R naught T, no change. We have RT, so the 0 went away, S naught R naught, and S naught T. So we removed this 0 from the expression statement. Theorem 14 is then applied. So if we look back now, we have T, R naught or R or S naught or SR. So what ended up happening is the T was pulled out from here and put outside of these parentheses. So then we have and then we have the R naughts together in that way, or the SR stays the same, but the ST then comes into the parentheses. We do that because then R naught and R are together, and we can apply theorem 8 to get T parenthesis 1 or S naught R naught. We can then apply theorem 6, which is going to give us, now I lost track of where I am. We can then apply theorem 6, which gives us T parenthesis 1 or S naught R naught. And then our final step is to apply theorem 2, which gives us T or S naught R. So we just went through a sequence using the 4 kind of steps that I had originally given, focusing on the parentheses, then doing the AND functions, then the OR functions, and applying those theorems in a sequence that gives us our final expression statement. Okay, so this slide looks at consensus theorem. Consensus means that you come to an agreement on something by definition. So if you look at theorem 16, 17, 18, and 19, they are saying that when we have a certain situation, it's equivalent to this. So in example, theorem 16 is x or x naught y is equivalent to xy. Theorem 17 is x naught or xy equals x naught or y. 18, we have x or x naught y naught is equal to x or y naught. And then theorem 19, of course, is x naught or x y naught equals x naught or y naught. So that is a consensus theorem. We've come to an agreement that if we have this situation, it is equivalent to this. So here is another example. This one is, again, walking us through. So this expression starts out with PS or PQS or PQS. So what we can do is my bad, the not lines got bumped off over here. So let me rephrase. This expression is PS or PQ naught S naught or PQS. We can start by applying theorem 14 to this. So then we end up with P parenthesis S or Q naught S naught parenthesis or PQS. We then can apply theorem 18. So we end up with P parenthesis S or Q naught parenthesis or PQS. Theorem 14 then gets applied again, and you can see theorem 14 actually gets applied twice in a row here. So the first time we apply theorem 14, we get PS or PQ naught or PQS. So we have essentially been able to distribute in a way that allows us to get down to 3 expression statements. Okay, so this is the last slide of the presentation, and you might want to grab a screen grab of this. This is all of your theorems that we talked about in this presentation. We also have a document inside of my MCPS classroom, so you can access this there as well. And I will see you in class for more practice. Bye.